This presentation is about a recent project that McHugh completed here in Chicago, and it's called Made to Order Success, the new McDonald's headquarters, global headquarters here in Chicago, and some interesting challenges that went along with it. So there's a good quote that I read in the ENR a few years ago. I thought it would be very relevant, but it says, for an industry founded upon solving problems, creativity is a quality that may well be as fundamental to projects as the laws of physics. As all of you probably know in various pursuits of your work and projects and stuff like that, creativity and problem solvings and working the problem are basically innate skill that we all have to be successful. So why innovate in design and construction? First and foremost, to build safer, to build better, and to build faster. So those are the three main premises to why we be pushing innovations and why we would want to do things differently than the way we've done them before. So just to talk about, give some kind of orientation on this project. This project, again, was located in Chicago. It's located in the West Loop area. So here's the downtown Chicago you might be familiar with. There's Lake Michigan here on the east, the Chicago River, the main branch, and then the north branch and the south branch. And just to the west of the expressway is the site location, 110 North Carpenter Street. It's notable that this site is rather famous. It was the former site of Oprah Winfrey's Harpo Studios, so a lot of people be familiar with that. What the project was, it was a new ground-up 9-story build-to-suit headquarters, 720,000 square feet, building that took up an entire city block. It's going to be retail, or is retail, along Randolph Street, and has got 2 levels of underground parking. The project, architecturally, is designed to reflect the surrounding areas. This was formerly like an industrial and meatpacking area or warehouse style type of buildings around there. So to express that vernacular, the architect basically tried to express columns and steel beams. This is all like just a facade. The actual structure is all cast in place, concrete. And here's a nice photo of the completed project. We're very proud of it, and the client was absolutely thrilled with the end result. But it was a challenge. Just some more background stuff. So the attributes, or sorry, the amenities inside there. So it's obviously being a global headquarters McDonald's, to have lots of collaborative spaces and stadium type seatings for presentations and just general the encouragement of the design was, or the design was trying to encourage these basically unplanned interactions. So lots of effort to create and design spaces like that. And so we got these central staircases to prompt pass-by interactions and conversations and little group huddle areas. There's a city view bar up there, and basically colleagues can meet and gaze upon the city skyline and come up with the ideas for the next Happy Meal. And so their headquarters city view wall. And of course, then there's, being McDonald's what they are, they have the McDonald's headquarters museum quality Happy Meal toy wall archive. So if you ever get to visit, this is quite the collection. And then they have various open plans and meeting rooms and phone rooms. So it's a very much a departure from the old style cube farm office type of environment. So the project statistics, the owner developer was Sterling Bay. The primary tenant was the McDonald's headquarters. They take over levels 2 through 9. The previous occupant was, as I said, the old Oprah studio. The project duration was 18 months, which was really compressed. Like I said before, the square footage was 720,000 square feet, 9 stories. Cost was $146 million, or $2 million per week. So a lot of activity, a lot of work was happening rapidly. McHugh's scope of work was core and shell, elevators with destination, dispatch, 9th floor build out, bathroom construction, the underground parking, and then landscaping. And the top-down construction was implemented. And I'll explain why that was chosen. So how do you build a burger? 2 all beef patties, special sauce, lettuce, cheese. If you guys are a certain age, you might remember that jingle. So basically, this whole project was all about the schedule. McDonald's made an announcement that they were moving out of their old western suburban headquarters, and basically had made a public statement saying that we're leaving, and we're leaving at a certain date. And then, you know, meanwhile, like, you know, where they're going to wasn't exactly 100% ironed out. So the developer had the site, and developer was trying to select a team. And so basically it was all about, like, you know, what team could meet the schedule and deliver a project for this, like, you know, literally, you know, world-class company, and get them a new office they can move in and not miss the schedule. So obviously, like, you know, the usual requirements of a project in terms of being cost competitive and quality all applied as always, but the big overriding goal of this project was the schedule. The schedule was everything. So the design team and the contractor were assigned early. All decisions were based upon the schedule, and the old saying, plan the work, work the plan, was critical. So keys to success, obviously, were the owner's priority. So complete the project on time, keep McDonald's happy, keep the neighborhood happy. So that was, like, you know, primary overarching goal. Milestones inform all decision-making. Remind the owner and the architect when design decisions were needed to keep the project on schedule. Remind subcontractors of upcoming milestones, inspection dates, etc. Always work with, not against. So again, everybody, and I have to give great credit to all our partners, they all took that to heart, and we all worked together to basically meet the goal. Just quickly, some of our project team members, obviously Sterling Bay, McDonald's, the tenant, Gensler, the architect, Magnuson Klemensic, the structural engineer, ECS, Geotech, Terra Civil, WMA, Civil, Wolf Landscaping, and then McHugh, general contractor, with Michaels, the foundation contractor, Collins Engineering, they were the ERS designer, and then lastly, Roy Strom, they were the excavation contractor who performed the top-down work, or excavation work. This is a Tekla model of the project, showing the complete cast-in-place structure with the drilled piers. So this is a structure. Being an office building is unique. It is entirely a two-way flat plate reinforced concrete slab office building. So this is you know, not your typical office building. But again, like, you know, compared to other structural systems, you know, with all the different parameters, it was definitely you know, evaluated and found to be the preferred and advantageous approach. So structural system selection, this was one of the, like, obviously most important, like, you know, and the earliest decision we had to get right out of the gate. So cast in place advantages, fast start and completion of construction, estimated to be starting 2 months quicker and to start, and 6 months faster to complete compared to traditional like, you know, structural steel and composite beam and slab on metal deck options. The real you know, advantage here was being the height of the building. Like, you know, we could basically detail and get rebar shipped to site in weeks, not months. And with our rapid cycles for pouring like basically a portion of floor every 2 days, we could basically complete 4 floors faster and get to the top quicker than if we the structural steel options. That proved for this building with this number of stories to be the advantageous choice. It was an economical a structural system, very, in terms of actual, like the structure itself was, you know, efficient design and very efficient to build, minimal lead times for materials. It matched the design aesthetic that the tenant was looking for. Again, they're in a like, you know, warehouse district of Chicago, having exposed concrete ceilings and drop panels and columns and stuff like that matched what the look that the design team was looking for. And also being an office building and an open plan with fewer partitions, this structural system had vastly superior sound and vibration control. Obviously, like, you know, as opposed to the lighter systems where they could be susceptible to footfall vibration and sound transmission. So the typical floor construction, basically it's as simple as you get for like two-way flat plate. You got the basically 30 by 30 columns. You got an 8-inch reinforced concrete flat plate with 14 by 14 by 16-inch deep drop panels. Concrete strength was 5,500 and about an average of 6 pounds per square foot. The typical bay was 30 foot by 30 foot, except for this area here, we had a longer span for 43 feet. So we accomplished that with a kind of a wide, like 20-inch thick, by 12-foot wide shallow beam along here to span that. And we had for lateral, we had a 16-inch core wall around the bank of elevators, and this wall here as well. These walls here also aided in the lateral system. But overall, very simple structure, and that very much played into the ability to build it quickly. So, and then for the top-down portion or the below-grade portion, level 1, this is the level at grade, was designed with the anticipation of the ability to build up and to build down simultaneously. So to achieve that, we had our 15-inch reinforced concrete flat slab. This slab was poured on grade, and it was also designed for the construction loads associated with the shoring and reshoring. Again, allowing us to build up with our shoring loads on this slab, meanwhile doing the top down. There's high strength puddling around the columns to aid punching shear, and then we had minimal beam framing. So for the most part, it was just basically flat plate. We had some beam framing around here for, we had basically it was a ramp to get down to the parking garage and some step down areas that required some beams. Obviously, doing a beam and a top down, you're actually going to have to excavate and then pour a mud slab that's going to be effectively the formwork to cast those beams. So minimizing that was critical. And also to allow the top down portion, the engineer gave us these 20 by 30 access holes, 4 of them, and basically 4 corners of the building to allow the excavating contractor to excavate, basically haul out material during the excavation process. And then lower level 1, so this is the level immediately below grade, was also a flat plate design, 10-inch flat plate. We had column capitals to accommodate the large spans, and those were just simple conical shapes that were easy to excavate, pour a mud slab that created that form and build that. And then again, we had these 4 20 by 30 access holes for the excavation. And then we had obviously the designer thinking about the process or how we're going to build it. That lent to their to the design. So they basically it was designed with top down or the methodology built in. So at the columns, these columns were actually like straight shaft caissons that were extended up all the way up to level 1. So we were able to basically have formed keyways that were constructed by Michaels, the caisson contractor, and then we just drilled in epoxy some dowels for that. This is here again, and this is what it looks like in plan. And then along the perimeter, we had secant piles. And again, at the correct elevation, we chipped in or saw cut and chipped in a new keyway and drilled in dowels. So again, this was all part of the design. And the engineer basically idealized this as a pin to accommodate that. Foundations and earth retention. There was 458 secant piles all the way around the perimeter and 100 caissons. And all this was done in 90 days. So a great testament to the accomplishment of Michaels and their crews and their equipment. The secant piles at the perimeter were 34-inch in diameter, and they were drilled varying from 40 foot to 100 foot and using specialized rigs. These walls were utilized kind of for double duty in various spots. Typically, they were used just as a foundation wall and the 2-story underground parking structure. And I got a person to raise the hand. So and then we had for the core, we had basically our sheet piling in the middle of the site for core and mat. And the foundations, here's the plan view showing it. So the secants all around the perimeter. And then here's where the ERS for the core around here. The foundations, like I said, were straight shaft, top of rock caissons, basically extending all the way down to our dolomitic limestone bedrock here in Chicago. They're about on the order of about 70 to 80 feet in length. They were designed to 180 KSF. This is beyond what the City of Chicago Building Code allows. So we did some O-cell or Osterberg cell load testing where they installed the O-cell at the base of one of the test caissons, and using, there's basically hydraulic lines and basically data lines coming up. And in that process, they use that hydraulic jack to attempt to lift the caisson up and measure consequently the bearing pressure on the bottom side of the plate, as well as get an indication of a skin friction of the shaft to the surrounding geotechnical layers. And then anyways, it more than proved out. The shaft was drilled under a slurry because we're basically we're not allowed. The way this was done was basically using continuous flight auger. So it was basically drilling using the slurry to hold the excavation. And then we had a 6,000 PSI concrete that was placed by Tremy to displace the slurry. And we obviously had our rebar cage in there as well. We were able to install a keyway on lower level 1 to basically help aid the top-down construction. You can see it right there shown. And the caissons for larger than 4.5 feet, we actually had a reduced shaft above lower level 2 to aid parking. So Michael's did a lot for us. Very accomplished in terms of their installation, and they showed their versatility to be able to accommodate top-down construction. The secant pile, like I said to you before, is basically a series of these circular shafts. There's the primary, which is unreinforced, and the secondary. In this case, we had this W24 section. This basically acts like kind of like a soldier pile and basically retains the earth. In various portions, though, we did actually extend the secant primary down to rock, so it could act as a foundation wall as well as basically a load carrying foundation wall, as opposed to just a foundation wall resisting lateral pressure. This is a plan view. This is an elevation view. Here's a section view. And we were able to, obviously in the top down, we were saw cutting in a keyway for the lower level 1 construction. And the top-down construction. So basically, what is top-down? And Stacy covered that as well. In the traditional approach, bottom-up, you'd have to basically construct all your deep foundations first, put an earth retention system around the perimeter, do a mass excavation to excavate your entire site, and then once you've got to the bottom of the hole, start building your way back up. And there's a significant amount of time in the schedule there. With the top-down construction, you can basically get started earlier on the above grade portions. So the sequence is a little bit different. So you're constructing your earth retention and caisson systems concurrently. You're installing your elevator core in a cofferdam, which is going to be constructed the traditional bottom-up method. But everywhere else outside of that coffer is being done from the top down. So you're constructing a level 1 slab that's on grade, that's being poured on a mud slab. And then once you've got that level 1 slab complete in portions, you can immediately start building up. And then meanwhile, all the activities that are going on below grade are detached from the critical path, and they can go on at their slower pace, and meanwhile not hold up what's going on above grade with the advancement of the tower going on above. So why do it? Primarily schedule. It saved 4 months on this project. It reduced the carrying costs and financing debt, and in general, bring faster to the market. But fundamentally, it saved schedule. This is an older photo, actually not from this project. This was another large top-down project that we did years before at the Block 37 site. But anyways, this is what it kind of looks like down there, where you've got basically large earth-moving equipment pushing material across to get it to the access hole so it can get out. So why do it? What's different? Construction sequences as discussed. The foundation ERS systems, they're going in concurrently, and the aesthetics. Obviously, there's aesthetical issues. The secant piles are exposed and left to view. This was again with the tenant and the owner. They were absolutely made aware. We took them to various projects where this was employed, and they were absolutely accepting of it. There's obviously the soffits, there's issues there as well. The soffits of the lower level slabs are basically created by the mud slabs. During the process of excavation, you have to basically scrape off those mud slabs. So there are areas where there were some scrape marks on there. We did our best to rub them out, but they're still there. And again, that was acceptable to the client. And then obviously you've got caisson shafts coming up. And again, they're in basically liners and stuff, and in certain locations, again, that was acceptable to the client. So challenges: there's complex sequencing. The secant piles retain the earth during excavation and in the final condition, so you're left with that. And then some structural redesign required. So modifications, or the engineer had to work with us and design the structure to accommodate the sequence. So they designed a level 1 that could take the shoring load. They designed basically access holes in lower level 1, level 1, and they had did some modifications level 2. And then the secant piles checked to transfer the base shear to the subgrade. So there was some additional analysis done there. And then water. Obviously, we're below the water table, so there's we had a sump system, but there is seepage. Between at some locations, obviously, did our best to mitigate that, but we did design a trough at lower level 1 and 2 to control that. And then obviously during construction, because we're using combustion engines, ventilation was a critical concern, and I'll talk a little bit more about that. Logistics plan, obviously big site, city block, 2 cranes. Very quickly, the 2 cranes going up simultaneously, so we had high one and a low one, and also being top down offered its own little challenges. The crane is the most important thing on a traditional cast-in-place structure. So the first thing that our concrete superintendent wants when he gets to the job is that hook. So this, and being top down, with a typical tower crane, you would put that foundation down here. Here, because we were starting off on level 1, we basically had it balanced on a portion of the level 1 a slab that we built, and then also it's supported vertically on the secant piles. So those secant piles supporting the tower crane, they actually went all the way down to rock. And this is some views of that tower crane. So this is a section view kind of showing a diving board. So it's cantilevered out past the public way. Basically the fulcrum of that seesaw is the secant piles, and there's a backup span to the first interior column. And we poured a portion of level 1 slab first, and then we poured a stub of the column passing through, and then we built the crane pad around that. Here's a plan view of this. So we had the secant pile here, we had one building column here, and then we're cantilevered out over the public way. Some more challenges. So again, further discussions about the ERS and foundations. And let me show you this. This is a video of basically a time-lapse video of the construction. Let's get this to play. So there's Oprah's Harpo Studios being demoed. And then our foundation contractor getting out there doing the secants as well as the straight shaft caissons and the ERS all at the same time. A lot of cranes out there simultaneously. And then straight out of the gate, our concrete team gets out and gets their tower cranes up. And meanwhile, they're off to the races going up, while over here you can see the excavation process taking place. So this is just a view of what we had to do to allow the secants to go in. So we cast in these guide walls with these foam knockouts. So basically we cast a wall here and here, and then the foundation contractor just popped out these, and then they knew that they were putting the secant in exactly the right location. I'm just showing them drilling through the guide wall. And then here's the core wall mat. So again, just traditional, basically core ERS system, cofferdam with whalers and cross struts or cross braces, and then us casting the mat and then just building up in a traditional manner. And then excavation. We had over 1,600 cubic yards of soil removed per day. That's 160 dump truck loads. So that's a lot of material being moved through the busy city streets. Spoil removal and recyclable material expectations versus reality. Obviously, this was critical for schedule to be able to keep a certain production rate. But for the most part, our projected production rate, as told to us by our excavation contractor, basically played out pretty well. Roy Strom has done a number of these projects with us in the past, so we had a good feel for what we could do, and actually they executed. There's challenges and safety hazards of obviously working underground in confined space, and maintaining schedule with equipment breakdowns and hauling and dump hours. So again, working through all that, we were able to meet the schedule. We had to obviously meet OSHA standards. So lots of procedures about tag in, tag out, monitoring air quality, and ensuring that we had a safe, well-ventilated, well-lit workspace for people. And again, I'll fly through this, but basically there's a lot of hazards. We obviously trying to meet all the OSHA requirements, had a lot of work for our safety department, but they did a great job, and we had no serious incidents or reportable injuries. So categorizing workspace, but basically we had this whole process of defining whether it was confined or not confined. Again, for the sake of time, I'll move along. You know, again, more issues with the excavation safety, but again, OSHA's got a lot of requirements in terms of monitoring and basically assessing like weather, like hazardous conditions. And again, we did everything we could to keep the production rate up and make sure we had a safe and productive below grade workspace. Atmospheric monitoring. Again, there was a big deal about keeping the ventilation there to make sure that we had less than 19.5% or more than 23.5% oxygen and 10.5% of basically other contaminants. Anyways, monitoring was continuous throughout the entire project. Employees cannot enter the confined space until atmospheric levels are within acceptable range or other controls. Working with our HVAC contractor, they did a great job of designing a system that was capable of meeting these criteria and kept us able to keep working down there. And so more about ventilation. And this was basically a quick calculation that we did for like the amount of equipment we down there, total horsepower, were like 913 horsepower, and the number of persons down there. And that it was you know, critical to make sure we had proper ventilation. Moving on, basically talking about the lower level excavation. We broke it up into 3 portions of excavation, but the level 1 itself, though, we broke that up into 7 pours plus these additional crane pours. So we started off here, over here, 1A, that was where the tower crane went. Then we popped over here to 1B, this is the second tower crane, and then we moved over here to level, this portion here, pour 2, and then we just basically hopped around and poured all these 7 sequences. Once we completed this whole top half, number 1, at that point it was the structure was complete, so we could begin the top-down process. And then once we completed everything from like 2 and 3, then the southern portion could begin the top-down process. So, but like at this point, once we completed 2, 3, and 4, they were going up and we were going down simultaneously. And then similarly for lower level 1, to excavate to get to lower level 2, we poured 1, 2, 3 as soon as we could, and then we moved down to basically 4, 5, and 6. But once we completed this top portion, this like mass excavation for lower level 1 could proceed. So again, we're constantly basically spreading out our workforce of excavation and concrete operations to keep just continual progress. And then just some photos of the excavation process. Like this is the initial process of excavating below level 1 to get to lower level 1. And then a earth mover just basically pushing material to the access hole to be hauled out. I just basically just comment here. This material here is like the famous Chicago blue clay. It's like Play-Doh. So just basically really, really soft. And then this is what the lower level 1 looked like after the completion of the excavation by the foundation contractor. So we would come down here, and our first step would be and then we see excavating the conical, basically drop panel around these columns. And so the first task for us would be to pour the mud slab that would be the form for lower level 1. And then this is another modification that required us to make to the building to allow the excavation. So this is level 2 right here. And obviously we have a long arm excavator that's got to reach down. So to allow that excavator to work efficiently and not smash into the building, we had to have a large block out on level 2. And then of shoring wise, we had to come up with a special shoring system to allow us to build over that and then reshore on top of that. And then again, just schedules, 18-month schedule, completion date remained the same despite scope changes, delays due to subs falling behind and lead times, and overtime, Sunday hours, holiday hours, all that stuff was being tracked and looked ahead to make sure we stayed on target. The neighborhood challenges, very briefly, must keep not only the owner happy, but also the West Loop neighbors. A lot of businesses, a lot of residences around here, plus other projects going on simultaneously. So being open, transparent, basically transparent and being communicative was critical to success. Some more facts and challenges. So concrete by the numbers, like we placed 38,000 yards, 3,100 tons of rebar, and 1.1 million square feet of formed surface, and 120,000 hours, concrete hours to complete. And so keys to success, like I said before, direct line to the architect and engineer, daily communication with the GC and other trades, site logistics and sequence. We were decking one half of the building while installing rebar on the other. So we had great efficient use of our labor. Mild reinforcing the decks, so again, very easy to install. And because this is an office building, minimal in-slab MEP. We typically do a lot of residential work where there's a lot of mechanical, electrical, and plumbing in the slab. This being an office building, not so much, so this basically allowed us to really build fast. And then our typical sequence for our office floors, we're like basically pouring, basically breaking this up into like bite-sized pieces on the order of like 12,000 square feet. So 1, 2, 3, and then zigging, basically come over here. So you're always decking, you're always installing rebar, and you're always pouring. So there's like, you know, every 2 days there's a pour. And then like, you know, basically level 7 to 9, we were basically like, you know, 4 2-day pours and then one day pour. So we were moving along. So again, basically our quantities here. And we optimize our shoring to allow the trades to quickly follow behind. So again, looking at the strength gain and doing our 347 SP4 shoring and reshoring, we're able to justify using 1 level of shores, 2 levels of reshores. Again, that helped us to get the exterior cladding up right as soon as we could. So again, helping the schedule. And our top-down sequence, like I said before, we're moving, basically right to left, 1, 2, 3, and then 4, 5, 6. And then these dimensions here was how far we had to go with our pump line. So we were basically 162 feet or so from the access hole. Some challenges, limited access. So everything had to get through these access holes. We stockpile material and then moved it over by hand from there. Pumping the concrete, unable to use the placing boom we normally would, so we had like basically rubber hoses to get us to where we needed to go. Longest pours were between 150 and 160 feet from the glory hole, and we utilized both hard pipe and slick lines to pour areas. And then connected from the top down to the coffer, we basically required like burning out the sheeting and then decking over here and then making the connection to the core. So again, once the ERS was removed for a level, the slab formwork supporting that was basically supported from the bottom up. And then some just close up of some details. This is us drilling in those dowels, the detail I showed you before. And then this is the keyway at the perimeter. And with that, I'll conclude my presentation because I think it went a little bit long. Oh, there's a question here I can answer. Did you use the maturity method to measure early concrete strengths? Emphatically, yes, that was absolutely the way we do it. Obviously the stripping the shores and cycling formwork were all strength critical operations, and we were definitely using the maturity method to make sure that we had the strength we needed to conduct those strength critical operations.